Alright folks, today we're going to talk about trends of the periodic table, things you notice about the way it is arranged, and we're going to talk about atomic bonds, how those atoms come together to form molecules. The periodic table, it was developed by scientists to highlight trends, to visually show you elements that have in common certain things and why they're placed together. So they're arranged in order of increasing atomic number. Atomic number is the number of protons in the nucleus. As you go across the periodic table, the atomic number is going up. They're arranged in order, adding one proton every time, which of course changes the element. Protons are responsible for the identity of the element. Periodic table is just a set of trends, repeating trends, the way it's arranged. From left to right across the periodic table, we go metals. The metals are all to the left of the zigzag line. This is the zigzag line once again. These are the metalloids on the zigzag line, sharing some properties with metals and some properties with nonmetals. And as we continue to move to the right, we have our nonmetals to the right of the zigzag line. As we go across, the number of valence electrons increases, remembering that group 1 has 1 valence electron. Group 2 has 2 valence electrons. Our pattern doesn't necessarily apply to these transition metals right here, so we pick back up with group 13, which has 3 valence electrons. Group 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has a full valence shell of 8 electrons. Across the table, number of valence electrons increases. As the number of electrons increases, the reactivity decreases generally, which means that these elements to the left of the periodic table are highly reactive, and these all the way to the right are much less reactive. Group 18 doesn't like to react with much of anything at all. As we go from the top to the bottom, atomic numbers and atomic masses increase. We're adding protons, adding neutrons, and they're getting more massive, right? And as we go down the periodic table through the periods, the number of total electron shells or orbitals or electron rings or energy levels, all those things mean the same thing. Those all are increasing. Period 1 has 1 total orbital. Period 2 has 2. Period 3 has 3. All the way up to period 7, which has 7. All right, so now it's important to talk about bonding. How do we create these molecules? We need to remember isotopes are atoms that have fewer or greater numbers of neutrons than they generally should. Ions are similar to that, only now we're talking about having more or less electrons, which is more important because electrons actually have a charge. Having more neutrons or less neutrons does not change the charge of that atom, but ions, the gaining or losing of electrons, does change the charge, right? Electrons are negatively charged, so when an atom gains electrons, which it has more negatively charged electrons than positively charged protons, so it actually has a negative charge. When an atom loses electrons, it has less negative electrons than it does positively charged protons, so it gains a positive charge. That is important because we know that negative and positive attract each other. So if you have a negative ion near a positive ion, they are likely going to attract each other. Very important for bonding, right? Atoms want to have a full valence shell. Okay, they want to feel full. Helium only has 1 shell. That inner shell can only have 2. So for helium to be full, it only needs 2. But for the rest of them, right, they want to be full. See, here we are. These are all full outer shells, full with 8 electrons, 8 valence electrons. Remember that valence shell is the outer shell, very important for bonding. So let's talk about ionic bonds. Ionic bonds. Obviously, these are going to be between the root word here, ions. Going to be between ions. Okay, if an atom has less than 4 electrons, they tend to lose them more easily, so that when they lose them, the shell that is left is full. If I only have 2 electrons in my valence shell and I lose those 2 electrons, they kind of go off on their own, go off to join another atom, then what I have left is that full shell of 8 electrons that was under that valence shell that only had 2. So when I lose electrons, once again, I become a positive ion. Okay, if I have 6 or 7 valence electrons, then maybe I gain a couple of valence electrons that somebody else lost. Okay, I gain extra negatively charged electrons. I become negatively charged, but then my shell is full. My valence shell is full. I feel better. And the charge of that atom corresponds to how many electrons it loses. If I lose 1, then I have a positive 1 charge. If I lose 2, I have a positive 2 charge. If I lose 3, I have a positive 3 charge. Okay? If I gain 1, I have a negative 1 charge. If I gain 2, I have a negative 2 charge. And if I gain 3, then I have a negative 3 charge, which is important because if I have a negative 3 charge, I'm probably going to be attracted to something that has a positive 3 charge. If I have just a negative 1 charge, I'm going to be attracted to another atom that has a positive 1 charge. And we're going to be attracted by those positive and negatives, making us stay together in an ionic bond. Positive and negative ions attract each other. They're bonded this way. It is once again an ionic bond. So let's look at a sodium atom. Sodium, as you can see here, has only 1 valence electron. This is our sodium atom. We've got 11 protons in our nucleus. We've got 12 neutrons in our nucleus. And we've got 11 electrons, 2 in the inner shell, a full 8 in the second shell, and then this just 1 over here. Sodium is a metal. It's on the left side of the periodic table. Metals are more likely to lose electrons. They're valence electrons because they often have less than 4. Okay, now we're going to look at chlorine. Chlorine is a nonmetal. Okay, here you can see chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons, right? 17 protons, 18 neutrons in our nucleus, electrons, 7 in that outer shell. Okay, it's more than likely going to gain an electron to make its outer shell full, making it Cl negative, making it a negative ion. So sodium has the 1 in its outer shell, right? It's going to lose that 1 and become a positive ion. You see that the electron goes off, and then what I have left is a full outer shell. So now it's a positively charged sodium ion. Chlorine, in a similar way. I gain that extra electron. You can see it here causing my shell to be full, but now I am a negatively charged chlorine ion. And they get near each other so that sodium loses its electron to chlorine. Sodium is positively charged, chlorine is negatively charged, and now the new molecule is neutral because the positive is attracted to negative when they're together. Since it's a positive 1 charge, a negative 1 charge, when they are together, it evens out so that you have now a neutrally charged molecule that was made out of a 1 positive ion and a 1 negative ion, causing them to stay together. And now you have an ionic bond between these 2 elements, creating a new molecule. You can also show it like this with our electron dot diagrams. And you see that sodium is positively charged, chlorine is negatively charged. They come together and stay together. You can also see it here. Boom, that electron goes right there, and here we are. Full outer shells and an attraction that holds them together as a molecule. You can do the same thing with something such as magnesium and oxygen. You see 1, 2, 3, 4, 5, 6, 7, 8. That's a full valence shell because magnesium has already lost 2 electrons. Oxygen here has gained 2, so your magnesium has a 2 plus charge. Your oxygen has a 2 negative charge. 2 plus, 2 negative, attracted to each other very strongly, creating magnesium oxide, which is once again neutral because 2 plus, 2 negative, it evens out, giving you a neutral molecule. Now we're going to talk about covalent bonding. Okay, much of the world is made up of covalent bonds. Covalent bonds occur between nonmetals. As we saw before, ionic bonds occur between metals and nonmetals. Covalent bonds occur between nonmetals, and they share valence electrons. So they're going to share them. So that valence electron is going to be orbiting, and it's going to spend some time around one atom and some time around the other, but it still is around both of them as it goes in its orbit, causing them to stay together because they're sharing that electron. Covalent bonds are shared valence electrons between nonmetals. So here we go. 2 hydrogen atoms. Hydrogen only has 1 shell. It also only has 1 electron. It wants to feel full, so it really needs to feel like it has 2 valence electrons because it only has that 1 shell. So here we have a hydrogen molecule, and these 2 hydrogen atoms are sharing their electrons, making them both feel full some of the time. Chlorine can do the same thing. Right? Chlorine has the 7. Both chlorine atoms have 7 valence electrons, and here they're sharing one of those valence electrons, so they both feel like they have 8. So we got chlorine atoms, right? These are their outer shells, just the valence shells here. We're just showing the valence shells. And then they come together, and it appears as though they both have 8. They feel like they both have 8, even though they're sharing that 1 to make it feel like they have 8. It's chlorine molecule, shared electrons. Each outer shell feels like it has 8 electrons. It is a covalent bond, right? Usually gases or liquids, they have low melting points, low boiling points because they're sharing and they're not really full. No electric charge. Molecules have no electric charge because we haven't gained or lost, we're just sharing. Same thing can happen between oxygen. There's our outer shells, just our outer shells, right? And these oxygens, they're going to share 2. They're going to share 2 to make them feel full. They're going to share 2 electrons. It can happen. Once again, still a covalent bond. Now metallic bonds. Metallic bonds are a specific kind of bond that happens only in metals. Metals have those few valence electrons, and they can still lose them easily. Okay, in this case, you get some metal atoms together, and those electrons kind of fly off and start moving around in what we would consider like a cloud. It would be like a cloud of electrons with all of the metal nuclei and the rest of their electrons in that cloud kind of floating around. Since they've lost some electrons, all those metal atoms are now positive ions. You've got your electrons floating around everywhere, and it's still, since the cloud is negatively charged, the cloud of electrons is negatively charged, the metal atoms are all positively charged ions. Everything sticks together because negative attracts positive. So it's like a cloud of things that are sticking together because of that attraction between positive and negative. Okay, this metallic bond, because it's kind of a loose bond, right? It's kind of a cloud of these positively charged atomic ions and these negatively charged electrons. Okay, it's what makes this kind of bond is what makes metals, so you can bend them and stretch them and do all the things that we can do with metals. It is this bond that is responsible for that, right? And it is this flow of these free-flowing electrons that causes it to be good conductors, because the flow of electrons is actually what electricity is. And so since they can flow so easily, that is why they are good conductors of heat and electricity. So this bond is responsible for the properties of metals. And here's another picture of this kind of sea of electrons floating around, and then you've got all these positively charged atomic ions.